So let's look now at trigonometric equations. And we're going to use trigonometric equations to solve for conditional statements and do solutions in what's called general form, and also involve angles that are numbers other than just theta, higher orders of theta. So a trigonometric equation is actually different from an identity. And it's different because an equation is true for some values in a variable, but not all the values. So it's not going to be true for everything, whereas an identity is true for all values. So when solving a trig equation, we can solve for a specific domain, and we're usually going to go between 0 and 2 pi, and we can also write it in what's called general form. And general form allows us to find any potential angles regardless of our domain. Basically, we can go around that circle as many times as we want. Well, let's solve this one. And to start, this should seem fairly familiar because we're trying to find secant theta when it's equal to -2 over root 3. And we did a whole unit finding these values. So secant theta, secant is negative, which means it is negative in quadrant 2 and 3. Cosine secant go hand in hand, and secant is the opposite of cosine. So secant theta is the hypotenuse over the adjacent. So that tells us that the hypotenuse in this triangle is 2 and 2. The adjacent is root 3, which means we have a 1, 2, root 3 triangle. Now, that's helpful because now we know our reference angle. And the reference angle in this case would be pi over 6. Now, once we have that reference angle, we can find whatever the angles will be. And so for part A, our theta values, and we can call them theta 1, is in standard position 5 pi over 6. And our other angle, standard position, 7 pi over 6. And that's part A, no different than what we've done already, finding those angles. Well, what about part B? We want to write this in general form. Now, general form is a little bit different because in general form, what we're not restricted to is hitting that terminal arm between 0 and 2 pi. We might get to that terminal arm by doing multiple loops around the circle. And if we do that, we want to write an equation that allows for those multiple loops. Well, general form is actually quite easy once we have the angles between 0 and 2 pi. So our theta 1, this time, we're going to use the information we had before. The first time we get to that terminal arm is 5 pi over 6. Now, if we wanted to get back to that terminal arm, we would have to go another full circle, another 2 pi. But we're not limited to 2 pi. We could do 2 pi, or add another 2 pi, and 4 pi, or 6 pi, or 8 pi. And how we say that is we say we want 2 pi n. And we're going to let n equal any integer. Remember our integers, plus or minus positive number. Remember our integers, plus or minus counting numbers. So if n was equal to 1, we'd be going around 2 pi. If n was equal to 2, we'd be going around 4 pi, etc., etc. So our second angle in general form, again, we take our angle in standard position of 7 pi over 6, and same thing applies. The first iteration is 7 pi over 6. If we do a full circle to get back to that angle, we add 2 pi. And we could add 2 pi or 4 pi or 6 pi. So really we're going to add that 2 pi n. Now it's very important that we include that 2 pi n, and also very important that we make that statement what kind of values n represents, integer values. So we have our solution over a certain interval between 0 and 2 pi, or general form. Now we're not restricted to solving trig equations to just theta. We're going to look now is what do we do when we're trying to solve a theta that has a coefficient? So a 2 theta, 3 theta, etc. Now the good part is we do very similar techniques. First thing we do is isolate for the trig function. Get the sine of whatever the angle is, like sine 2 theta. Once we have that 2 theta, then we determine the general solution for 2 theta. And once we have it solved for 2 theta, then we're actually just going to divide by that coefficient to get it down to just a theta value. And once we have it down to a theta value, then we can determine whatever values we want for a specific given interval, like 0 to 2 pi. So really the only difference is we find the general solution first, and then we find the specific or the conditional solutions for an interval. So let's put it to practice here. Let's figure out where is sine 2x equal to -1. So our first step is solve for the trig identity, which it already is. Sine 2x is equal to -1. So now what we want to do is we want to figure out, all right, what values, if we imagine this as sine theta, would equal -1. Well, where would theta equal -1? Well, this is pretty straightforward. We can use our quadrantal angles. Sine of theta is equal to -1 down here at 3 pi over 2, and our theta value would be 3 pi over 2. Now, that would be what the angle would be if it was theta, but our theta is not 3 pi over 2, it's actually 2x equals 3 pi over 2. Now, again, that's not the general solution. We want to figure out how could we get back to this value, and if we think in standard position, the first iteration is 3 pi over 2. Then to get back there, well, we need to do a full loop. So we'll need to add 2 pi, and then we get that n. Well, there's our solution for 2x, but that's not the solution for x. We want to solve this for x. And this is where we take our 2x and divide everything by the coefficient. We're going to divide everything by 2. And what that's going to do is make an equation where x equals 3 pi. Remember, if we divide that by 2, same as multiplying by a half, 3 pi over 4 plus pi n. And there is our general solution. Remember, where n is an integer value. And because we have 2x, we start with the general solution. So now how do we do part B? So in part B, what we're going to do is now use the equation. Use the x equals 3 pi over 4 plus pi n, and we're going to generate our solutions using this equation and plugging in values for n. So let's just start with n equal to 0 because that's the easiest one. When we put n equals 0, we'll get our first x solution, and it's pretty easy to see. We get 3 pi over 4. The n equals 0 just cancels that out. Well, what about when n equals 1? That'll generate our next solution. x2 then will be 3 pi over 4 plus pi times 1, which is really just pi. And we know that that becomes 3 pi over 4 plus 4 pi over 4, which is 7 pi over 4. Now, all we have to do, though, is check, does 7 pi over 4 fall into that interval? Does it fall between 0 and 2 pi? And of course it does, because if it didn't, it would have to be smaller than 0 or larger than 8 pi over 4. So there's our second solution. So let's try n equals 2. When we put n equals 2 in there, we'll get 3 pi over 4 plus, and here's our big clue, 2 pi. Now, if we add 2 pi to pi over 4, we know when we check between 0 and 2 pi, it's going to be too big. So n equals 2 is too high, so it doesn't work. So that tells us that our only solutions that fall between 0 and 2 pi are the two we've generated, 3 pi over 4 and 7 pi over 4. And there are the solutions. So we could solve for any coefficient. We first find the general solution, putting in that n as an integer, and then we generate our values from that equation. And we're going to do a number of questions like that with higher coefficients as we work our way through these questions in class.